Hi everyone. In this video we're talking about local and global extrema. And by extrema I mean minimums and maximums. Now you've probably seen some of this stuff in a previous math class before, and so you can take a moment to consider this first example and tell me, on this blue curve, where do you see a local minimum and where do you see a local maximum? Well, the local maximum is going to be right here, and the local minimum is going to occur right here. Now, these are called local minimum and local maximum because if you look at just the little neighborhood surrounding the point, this point is going to have the largest value, right? The function has its largest value at that point, compared to just the sort of small neighborhood of input values around that region. And same thing over here with the local minimum. I'm calling this point here my local minimum because when you compare it to just the points that are just next to it, that point gives the function its minimum value. And I specifically call these local minimum and local maximum because you'll actually notice that there's places over here where the function is greater than that maximum, right? And we see places over here where the function is actually less than that minimum. However, just in the local region around those points, we find that they are minimum and maximum. Now, you might take a moment, pause the video, and look at this red curve and tell me where is the local minimum and local maximum. And you'd be correct to say in this case that this red curve doesn't have a local minimum or a local maximum. In fact, this red curve everywhere in the entire domain is going to be increasing. And so whenever we have a red curve like this, or we have a function that's increasing over its entire domain, we say that it is strictly increasing. Now, last lesson we learned about critical points. And I want to point out this fact here, that any local minimum or local maximum, it must occur at a critical point. And think about why that might be. A critical point, like we learned about, is a point where the first derivative is equal to 0. But if you remember that the derivative is the slope of the tangent line, and you sort of imagine the tangent lines here, over here the tangent lines are going to have positive slope, and over here the tangent lines will have negative slope, and over here the tangent lines will have positive slope. And between those, right at those maximums or minimums, your tangent line would have 0 slope. You'd have a horizontal tangent line there. And so this is why the local max and local min, they have to occur at critical points. So we remember, we have an interval of increasing, followed by an interval of decreasing, and right in the middle, that's where we have a point where it's neither increasing nor decreasing. And after you get done increasing and you're ready to start decreasing, that naturally forms a local maximum. And you can use the same logic regarding the local minimum. Whenever you're done decreasing and you're ready to start increasing again, you have to pass through a point where we're neither increasing nor decreasing, and that naturally forms both a critical point and the local minimum. Okay, so here's a little bit more formal definition. A local minimum is a point in the domain of a function where the first derivative is equal to 0 and the second derivative is positive. Or we could also say the second derivative is greater than 0. So in other words, if the second derivative is positive at a critical point, then that critical point has to be a local minimum. And so if the second derivative is positive, what does that mean? That means that the first derivative is changing so that the first derivative is becoming, well, first of all, less negative, And then after it passes through 0, you might say it's more positive. So the first derivative is increasing. And if the first derivative is increasing, that must mean that the second derivative is positive. And that's what makes a minimum. A local maximum is going to be a point in the domain of a function where the first derivative is equal to 0 and the second derivative is negative. In other words, if the second derivative is negative at a critical point, then we know that critical point is a local maximum. And why, for a local maximum, would we say the second derivative has to be negative? Well, if the first derivative is like the slope or the steepness of this curve, you notice at first the slope of the curve is becoming less positive, and then in the end the slope is becoming more negative, you might say. In other words, you might just say that the slope is decreasing, or the first derivative is decreasing around where we have a local maximum. And if the first derivative is decreasing, that means your second derivative is negative. So hopefully that makes sense. A few more definitions. I know there's a bunch of new vocabulary words here, but the word extrema refers to the set of all extreme values of a function, which might sound redundant, but extreme values include all of the local minima and local maxima. So it's kind of an umbrella term, right? So like this is extrema, and extrema is divided into both local mins and local maxes. Extrema is just, like I said, it's an umbrella term that describes both minimums and maximums. Okay, now let's talk about global minimums and global maximums. A global minimum is a local minimum which is also the lowest possible value from the function. There might be multiple local minima with different values, but there can only be one value for the global minimum. Although it's actually possible to reach that global minimum at multiple places in the domain. So this is synonymous with absolute minimum. So absolute and global mean the same thing. You might see either one. Likewise, a global maximum has practically the same definition. A global maximum is just a local maximum, which is also the greatest value possible from the function. So there may be multiple local maxima with different values, but there may only be one value for the global maximum. Although it's possible for that global maximum value to occur at multiple places in the domain, and absolute and global mean the same thing. So global maximum is synonymous with absolute maximum. Notice in general, when you're asked for a minimum or maximum, you should answer the question with a coordinate pair. So a coordinate pair means give the x value, put a comma, and then give the y value. So this gives you both the x value and the y value for the extreme point. I've noticed that some teachers ask the question expecting the x value, and some teachers ask the same question, but they expect the value of the function, or the y value. So it's just good practice to give the more complete answer, give both. Both find where in the domain that maximum or minimum occurs, and find what is the value of the function when you reach that extreme value. So here's some examples, and they're, kind of thought-provoking examples. What are the local and global extrema? What are the local and global extrema of the curve shown below? So here in purple, I have this nice curve that represents some function, and here I see a local maximum. And here I see some kind of minimum, and there I see another minimum. This is a case where this is only a local maximum because I have values over here that are greater than that local maximum, but there's really no absolute maximum, and there's no global maximum, in other words, because this function keeps increasing on the right and it keeps increasing on the left. So, in other words, no absolute maximum, but we do have a local maximum. there is only one value of the function which serves as the global minimum, but it occurs at two different places in the domain. So notice these values are the same value, but it occurs at two different places in the domain. So those are kind of both the global minimum, which is kind of weird. In our next example, we have this. You'll notice that this particular curve representing some function has no minimum anywhere because it keeps going down on the left and it keeps going down on the right. So there's no minimum, local or global, that we could point to. This point right here is both a local maximum and the global maximum of this function. However, this is not differentiable here at that point. Remember, when we have pointy functions, that point where it's pointy is not differentiable, which means you cannot take the derivative there. So if you can't take the derivative, that sort of means that the derivative is also not zero, because it doesn't even exist. And so my point is that sometimes you can have a maximum in a continuous function at points where the function is not differentiable, in addition to critical points. So I guess what I should have said, maybe I was oversimplifying, where it says any local minimum or local maximum must occur at a critical point. This really should say any local minimum or local maximum of a differentiable function. Must occur at a critical point. Because if you have a point in your function that's not differentiable, that might be a local maximum or a local minimum. That's also not a critical point because it's not differentiable there. Okay, so I'm glad I had that example so I could clarify that point. Here I have a piecewise function. We call this piecewise because my function definition comes in two pieces. One piece describes what happens when x is less than or equal to 1, so during this part. And the other piece of my function describes what happens when x is greater than 1, so for this part of the domain. And what I want to point out here, what do I see? I see a local max here, which does not occur at a critical point, but also my function isn't even continuous here. So this is a discontinuity there. So if it's a discontinuity, it certainly is not differentiable. So I have a local max, and I also have a kind of what looks like a local minimum. And I want to point out, though, that this local maximum happens to occur when x is equal to 1, because x equals 1 belongs to this first piece. X equals 1 belongs in the interval where x is less than or equal to 1. But if you were going to tell me that this is somehow a local minimum, because that's what it looks like, if you're going to tell me that, I would actually tell you that you were wrong. That this point right here is not a local minimum. And the reason is a little bit technical, but this piece of the function right here only applies when x is greater than 1. And so if you told me that this looked like a local minimum, I would ask you, well, where does that minimum occur? In other words, what is the x value? If you told me that the local minimum was at x equals 1, well then no, that would actually belong to the left piece of the function. That would be the local maximum, so this would be no. What if you told me that this was at x equals 1.01? Well, I would tell you no again, because the point at x equals 1.001 has actually a smaller value of the function. And so that is also not the minimum, because what about x equals 1.0001? Well, no again, because I can always move a little bit to the left and find a lower value of my function. And so there is actually no local minimum here. Even though it appears that there might be a local minimum, you have to look closely at where the piece of the function actually applies. Okay. Hopefully that clears some things up and doesn't overcomplicate things. And I'll see you guys in the next video.